Welcome to today's Explainer. We're digging into a seriously fascinating debugging mystery straight from the programming notes of a developer named Ang. You know that feeling when you've got a perfectly good piece of code, you tweak it just a bit, and suddenly it completely ruins your final output? Yeah, we've all been there. Today, we're going to look at exactly what went wrong during what seemed like a totally routine Haskell refactor, and more importantly, exactly how to fix it. Okay, let's dive into this. The big question we're looking at is, why did our Typst links suddenly turn into raw text? Picture this. You've just wrapped up what feels like a wildly successful code refactor. The architecture? It's cleaner. The logic? Super tight. And your compiler isn't throwing a single error. It's a great feeling, right? But then you open the final PDF that your app just generated, and it is a total disaster. Your nice, clickable document links are just gone, completely replaced by this jumbled, unreadable mess of raw markup. No way. So, to understand how a disaster like this actually happens, we really need to map the territory. Our data pipeline here is basically a multi-step transformation. First up, we've got Haskell tokens providing the raw logic. Then, those get converted into a Pandoc abstract syntax tree, or AST. Pandoc is basically acting as our middleman here, translating that AST into a Typst document for modern formatting, and then that finally renders out the finished PDF. So, it stands to reason, if something breaks at the very end of this chain, the culprit is hiding in one of these handoffs. The whole situation actually started with a super relatable developer urge: optimization. The initial goal here was simple: efficiency and token mapping. In the original version of Ang's Haskell code, there was this isolated, entirely separate function that was specifically dedicated to handling Typst indexing. But let's be real, running a completely separate pass just to index keywords, it's just not the most efficient way to process data. So Ang realized that this redundant function could be scrapped entirely, and its logic baked right into the primary token mapping phase. Let's look at the actual Haskell diff. But for the change, we had the indexing code just sitting there as a standalone function doing its own separate transformation pass. But after the refactor, that standalone function is entirely gone. The logic is so gracefully integrated into the main function. Angst uses a where clause to pull out keywords from the metadata and a transformation step to apply the index directly as the paragraph tokens are being processed into blocks. From a software engineering perspective, this is a beautiful consolidated refactor. And logically speaking, it compiled flawlessly. But that beautiful, clean code ran straight into a brick wall. Here is the plot twist, captured directly in Ang's own notes. Quote, "During the refactoring, I discovered another bug with the conversion during manual testing." Yep, despite functioning perfectly on a purely logical level, manual testing exposed a massive flaw. The tokens were mapping, the program was running, but the actual physical document generation at the very end of our pipeline was completely broken. Think of this as the overzealous translator problem. The intended output was supposed to be an active, perfectly formatted Typst index link, something a user can actually click to navigate around the PDF. But what Ang's PDF actually looked like after the refactor was literal, broken text just vomiting pound signs and angle brackets directly onto the page. The Typst indexing completely failed to render. The visual output was, to put it mildly, an absolute disaster. So the crucial point is, who is the culprit here? Well, it wasn't Haskell doing the math wrong, and it wasn't Typst failing to render what it was given. Nope, it was Pandoc, our middleman. Pandoc was acting like a hyper-vigilant security guard. It saw these special characters, the pound sign, the less than sign, the greater than sign, and basically said, whoa, hold up, this might be dangerous or unintended markup, let's escape them. It treated these specific characters as literal text, slapped escape codes on them, and thereby entirely destroyed the syntax that Typst needed to actually recognize the link. Essentially, Pandoc protected the text so much that it completely broke the underlying code. To fix this mess, Ang couldn't just magically change the Typst syntax, and obviously dropping Pandoc for the document conversion wasn't an option either. The fix required a very specific, targeted intervention, using raw inline functions. We basically have to give Pandoc a VIP pass for these specific strings of text. We have to force it to back off and recognize that this index markup is actually raw Typst code, not just standard everyday text that needs to be escaped. Enter our technical intervention, raw inline. This is a function specifically used to stop Pandoc from escaping special characters, which ensures raw Typst code remains completely intact. By wrapping our carefully constructed Typst index strings in this specific function, we are explicitly telling the Pandoc's ASD, hey, do not touch this. Do not translate it, absolutely do not escape it. Just pass it through exactly as it is. It acts as this impenetrable protective shield against Pandoc's aggressive escaping behavior. And this brilliantly illustrates the exact replacement logic that saved the day. We start by pulling a keyword right from the metadata. Now, by wrapping that raw Typst output, which includes the #, index, the keyword, and the link logic, inside our raw inline shield, the entire string passes safely through the translation step. It arrives in the Typst document perfectly intact. Typst finally sees the #, recognizes it as a system command like it's supposed to, builds the index, and creates the active link. Boom! The pipeline is officially restored. But, let's zoom out from the specific Haskell code for a second here. What Aang experienced isn't just some weird quirk of Pandoc or Typstis. It highlights a much broader, universal software development lesson: the manual testing mandate. It is so incredibly easy to get caught up in the cleanness of a refactor and seeing all those nice green check marks on a fast test suite that we actually forget the ultimate goal of the software we're writing in the first place. I really want to draw your attention to Aang's ultimate conclusion here. To quote the notes, "And while we can write automated tests to cover this behavior, manual testing is still absolutely necessary to ensure the indexing actually renders and works correctly in the final generated PDF document." I mean, that is a profound reminder for anyone building automated document pipelines. Automated tests, they are fantastic for verifying logical rules that guarantee that function A calls function B. But human eyes, they are absolutely required to ensure visual rendering actually works as intended. An automated test can't always tell you if a document looks broken to a reader, it only knows if the underlying data string matches. Which brings us to our final thought for today's explainer. If your automated tests pass, but your PDF looks wrong, did your code actually work? It's a pretty provocative question, isn't it? It really challenges us to reconsider where our document automation pipelines actually end. Do they end at the terminal output, or do they end when the human user actually reads the physical page? Definitely keep that in mind the next time you're refactoring your own data pipelines. Thanks for joining me on this deep dive into Aang's Haskell notes, and I hope you leave today with a fresh perspective on debugging in the undeniable value of just trusting your own two eyes.